Great. Yeah. Okay, so maybe it's 8 sharp. Shall we start? Yeah.
Okay.
Okay, great. Okay, so so today's Global Poisson. We're very happy to have Professor Liu Zhangju from Beijing University. So he will give a talk on Atiyah classes for generalized holomorphic vector bundles. Professor Liu, please.
Okay, thank you very much. And thank organizers for inviting me to give a talk here. Okay, the title of my talk is Atiyah classes for generalized holomorphic vector bundles. So this is joint work with Lang and Jia. So Atiyah class of holomorphic bundle on a complex manifold was first constructed by Atiyah is obstruction of the existence of holomorphic connections to glue local holomorphic connections to a global one, give rise to a one cocycle in then a cohomology class in Cech cohomology, which is also equivalent to the extension class of the first jet bundle. The notion of Atiyah classes is also introduced by Chen, Stienon, and Xu in framework of Lie pairs, which include the Molino class for regular valuation of manifold in the characterizes the existence of invariant connection on a homogeneous space. In this talk, we introduce Atiyah class, which is obstruction of the existence of generalized holomorphic connections for generalized holomorphic bundle on the generalized complex manifold. Everything is generalized here, but it will be saying that the generalized holomorphic bundle here is not more it is just special case of that in the sense of Goreto, just called macro, similar to the Marco, that Marco, this Chinese name is Gualtieri. This
really
similar to the homological case, such Atiyah classes can be defined by three approaches: Cech cohomology, extension class of first jet bundle, as well as the Lie pair. So this is the plan of this talk. First, introduce Atiyah class for holomorphic vector bundle, and second, review generalized complex geometry, and then study generalized holomorphic vector bundle on the generalized complex manifold, and finally define Atiyah classes. So first, recall that the original Atiyah class. So a complex vector bundle E on M is a complex on the complex manifold. Manifold is a holomorphic bundle if there's open cover in the family of holomorphic local trivialization. That is, each phi I is holomorphic diffeomorphism. This is a definition of holomorphic bundle on the complex manifold. There are also two equivalent definition of holomorphic bundle. The first is there exists a local trivialization such that corresponding transition functions phi ij are holomorphic functions. That is, all transition functions to glue the vector bundle are holomorphic functions. And another way is if this complex vector bundle. This has a flat T01M connection on E. Here, T01M denotes the Lie algebraic of anti-holomorphic tangent bundle M. That is, there is a Lie algebraic connection, which is flat. Locally, this flat connection constructed as follows. Take a frame and define the connection just by a partial bar, the function. Here, we use the same notation for partial bar for Dobu differential operator in this flat connection. So this connection is flat since the partial bar square is 0. In fact, the above construction is unique in the sense that if one has anti-homology connection T01 on the complex vector bundle, then there exists a unique holomorphic bundle structure on total space E such that D01 just equal a partial bar. So this is a 3 equivalent definition of a vector bundle on the complex manifold is holomorphic. So now later, Kelly OM denotes the shape of local holomorphic functions. A section S from M to E is holomorphic if partial bar is 0. That is which is a shape of module over OI. So not so definition of holomorphic connection. Later E, a holomorphic bundle on the holomorphic manifold M. A holomorphic connection on E is a linear map. We use shift language here. D from E to omega M tensor E. Here omega M is a holomorphic one form on M in the E considered the holomorphic section of E. Satisfy the following Euro condition of a connection. So this connection, that is this holomorphic connection D send the holomorphic sections of E to holomorphic sections of holomorphic one form tensor with holomorphic sections, or equivalently for any holomorphic vector field X, the covariant derivative dx preserves holomorphic sections of E. This is equivalent condition. So locally, a holomorphic connection is always exacted, is in the form partial plus A, where A is a metric valued holomorphic one form. Thus, D plus capital D plus partial bar equal D plus A. Here, D is Euro exterior differential on M. D plus A defines the ordinary connection on E, but in general, 1,0 part of an ordinary connection on the holomorphic bundle is not necessarily a holomorphic connection. The obstruction is the Atiyah class discussed below. So let E be a holomorphic bundle on a complex manifold with local trivializations. So a local holomorphic connection on UI cross CR is in the form partial plus AI, where AI is a matrix valued holomorphic band form on UI. They can be glued to a global connection on E if in the only F there are following equations on UIJ or equivalent in the following form. Note that the left side of this equation is independent of the connection matrix AI by the relation phi ij, phi jk, phi ki is equal 1. This is a co-cycle condition. We can it can be found that the left side is always is a Cech 1 co-cycle with coefficient omega m tensor and E. The right hand side is a co-boundary. If you is in this frame, we take it delta A, where A is a 0 co-chain of Cech complex. So if you have a global holomorphic connection, the left side, this co-cycle is exact. So the definition of class. So the Atiyah class AE in Cech cohomology group of holomorphic bundle E is given by Cech cocycle, just left hand side above equation. So Atiyah proves that in his paper, Atiyah proves that a holomorphic bundle E admits a holomorphic connection if in the only if the Atiyah class AE is trivial. So this Atiyah class defined by Cech cohomology. The Atiyah class may be also defined by means of curvature of Chen connection in the double cohomology. So let E H be Hermitian holomorphic vector bundle on M. A connection nabla on E is called Chen connection. If nabla H equal 0, that H is parallel, and the 0, 1 part of this connection is just a partial bar. That's partial bar, the operator, where nabla split into nabla 1, 0 and nabla 0, 1, the holomorphic park in the anti-holomorphic parks. The curvature of Chen connection F nabla is a two-form 1 type, two-form matrix value. And by Bianchi identity, we have partial bar F nabla is 0. So therefore, this gives a double cohomology class F nabla square bracket. The proposition is that for curvature F nabla of Chen connection on a Hermitian holomorphic bundle, vector bundle, EH, one has this class is equal to just Atiyah class, since these two identify this double cohomology group in the Cech cohomology group. So this is another definition of Atiyah class by differential geometry language. Of course, this class is independent of the Chen class in the Hermitian matrix. Yeah. So this is a brief review of holomorphic vector bundle in the Atiyah class by two approaches. In the another way is by extension class with we'll discuss later. So now we have great review about for generalized complex geometry. For n-dimensional smooth manifold M, there is a canonical inner product of signature NN on generalized tangent bundle Tm direct sum with T star M with the canonical inner product and Coulomb bracket on sections of tangent, generalized tangent bundle of M. It's knowing that this bracket is not, doesn't satisfy Jacobi identities. In fact, it's a Lie-2 algebra. This is the basic properties of Coulomb bracket with anchor. This anchor is just projection from generalized tangent bundle to tangent bundle. So the build T is generalized tangent bundle in, and it is knowing that T with Coulomb bracket standard inner product inner product in the anchor is a standard Coulomb algebroid. This algebra, which is the starting point for generalized geometry. So this definition of generalized the manifold, a generalized complex structure on M is the endomorphism of Carly-Jeff generalized tangent bundle, such that J square equals minus phi. The key in the product is invariant. Keep the inner product, the eigenvalue of I, L positive in the plus in the minus closed under Coulomb bracket. This is integrability condition. Note that L minus equal complex conjugate L plus in the intersection of L plus and L minus 0. Moreover, T and L plus L minus forms a Manning triple. That is, the pair L plus in the L minus is a Lie algebroid by identifying L plus in the L minus star. Then one gets to the algebra differentials L plus in the D plus in the D minus, in the induced Prosum structure by Lie algebroid structure on base manifold and on base manifolds. So important feature of generalized geometry is there is a B field transform EB is automorphism of Coulomb algebroid given by a two-form, a closed two-form defined as follows. Let's keep everything is invariant of Coulomb algebroid. So there's an element of symmetric group of Coulomb algebroid. So after B field transformation, a generalized complex structure is still a generalized complex structure. So B field transforms thought is a gauge transformation. So every reasonable properties structures should be invariant and B transformation. So now we define the basic objective of a talk is function of smooth function on the generalized complex manifold is called a generalized holomorphic function if D minus F equals 0. So this definition is reasonable since it is invariant and the B transforms. Suppose if is a generalized holomorphic function D minus F equals 0. So both X in the set 0. So after B transformation for new generalized complex structure DBL minus F equals X plus psi plus contraction B by X, this is also 0. So for new generalized complex structure, F is also a generalized holomorphic function. So this is reasonable for definition of generalized holomorphic function. So generalized holomorphic functions are Gaussian function for Poisson structure induced by Lie algebra structure. So D minus G is 0. Third, denote by same OM is the rank of local generalized holomorphic function on M. By definition, the OM is kernel D minus. That is, it's the kernel of differential operator. So it is a subsheaf of sheaf of smooth functions. So by these properties, that we can use the sheaf language to describe anything, some things. So the sheaf language is a more flexible language than differential geometry language. Don't need, it doesn't need regularities. So right in the morphism on generalized tangent bundle in block form. So this component should satisfy some compatibility conditions to get a generalized holomorphic structure, a generalized complex structure. There's 3 typical examples. The first is the Fj is in the morphism T, it is diagonal. So this diagonal matrix is a generalized complex structure. If in the only Fj is complex, is ordinary complex structure on M, its eigenvalue L plus is holomorphic tangent bundle in the anti-holomorphic cotangent bundle in L minus is a complex conjugate is anti-holomorphic tangent bundle in the holomorphic cotangent bundle here. D plus equals partial in the D minus equals partial bar, just to double differential operators. So that generalized holomorphic function is just the holomorphic function. In this case, OM just a sheaf of holomorphic functions in the induced Poisson structure on M is trivial in this case. So second example is for invertible two-form omega. This defined the endomorphism on is a generalized complex structure if in the only if omega is simplistic structure on M, the minus I eigenbundle L minus is a graph. It's a graph X plus I omega, graph of I omega. In this case, D minus just D, the exterior differential on M, and D plus is 0 in this case. Thus, the function is generalized holomorphic function if it is constant. Df equals 0 is the local constant. In this case, omega OM is a constant shift, the trivial shift, and the induced Poisson structure on M just that one coming from symplectic structure. So another example is holomorphic Prosum. It is that MG is a complex manifold, and the beta is a bivector field. That in the morphism, Kali G is in up triangle form, is a generalized complex structure. F in the only F, pi defined equals J composed beta plus I beta is a holomorphic Poisson structure. That is a partial bar pi equals 0. There is holomorphic in the Scotten bracket, pi is 0. So in this case, L plus is the holomorphic tangent bundle plus graph of beta plus of beta. So in this case, D minus F equals partial bar F minus 1/4. This is Hamiltonian vector field of F. So hence, F is a holomorphic function. F in the only F is a holomorphic Casimir function. So this part 0 means holomorphic, and this part 0 is Casimir. So for holomorphic Poisson structure, generalized holomorphic function is holomorphic Casimir function. Now this is a generalized double theorem. Roughly speaking, around a regular point, a generalized structure manifold locally equivalent to a complex manifold product cross with a simplex test code. This equivalent sometimes called the Courant equivalent. That is up to a diffeomorphism of M in the B transform. So in a regular case, we have the generalized double coordinates J, P, Q. So in this case, a function is generalized holomorphic F in the only F. Partial F partial J bar equals 0. That is in the F independent of P and the Q. So F just function of Z, a holomorphic function of Z. In general, a generalized manifold is locally always equivalent to product of homological Poisson manifold and the symplectic manifold. This Bailey's result is maybe in PhD thesis, so that generalized holomorphic function in locally is equivalent to a holomorphic Casimir function. So now we define holomorphic vector bundle on the generalized general complex manifold. Suppose that definition. So suppose that M is a generalized complex manifold. A complex vector bundle of E on M is called a generalized holomorphic bundle if first E itself a generalized complex manifold, and the second there is open cover UI in the family of local trivialization phi I such that for each I, phi I is a generalized holomorphic diffeomorphism. Here, UI cross CR is equipped with a standard product generalized complex structure. This is the complex structure. This on UI, this open site induced induced from M, a general complex structure is an open site. Here, a generalized holomorphic morphism is defined by this F is a map from between two generalized manifold. Thus, the tangent map is commute with generalized complex structure. This is a standard definition. So such kind of local trivialization we call a compatible local trivializations of generalized holomorphic bundle. So like similar to the ordinary holomorphic case, there is a different definitions for generalized holomorphic bundle. So roughly speaking, so proposition is starting from a real vector bundle on a generalized holomorphic manifold with a family of trivialization in the transition matrix phi ij. Then E is generalized holomorphic bundle with compatible local trivialization if in the only F phi ij is a complex matrix. Not complex matrix is a subgroup of real matrix. This R by R, this is 2R by 2R. That is, E is a complex vector bundle. Second condition is each component A lambda mu of transition matrix phi ij is generalized holomorphic function. So therefore, condition 1 and 2 can be used to define a generalized holomorphic bundle. This is the equivalent like ordinary holomorphic case. Each transition functions, the holomorphic functions. Now, transition functions are generalized holomorphic function. So let's skip so by commuting, this is the commuting relation. Finally, this gets this. This means the condition 1 and 2. So now we see example. So a generalized holomorphic bundle on the complex manifold is an ordinary holomorphic bundle, since the transition functions are holomorphic functions in this case. A generalized holomorphic bundle on a simplistic manifold is a complex vector bundle with a flat connection, since transition functions are constant functions in this case. This is a two typical case. Next, we'll see holomorphic Prosum case. So first, recall the Prosum module. This is in sheaf case. A Prosum. This is the Prosum algebra acts on the sheaf of holomorphic sections. A section of vector bundle. In fact, just say this definition, the differential geometry language. So a vector bundle a Prosum module of a Prosum manifold is just a module of Lie algebraic, cotangent Lie algebraic T star pi m. This is this cotangent this Lie algebraic comes from the Prosum structure of M. So proposition this but we can any generalized holomorphic bundle on a generalized complex manifold is always a Prosum module for Prosum structure induced from Lie algebra structure. Defined it follows. After trivialization, take a frame bundle, so each section is the sum of smooth a function in the basis. So this defined the action f on S is just defined by Prosum bracket. So this is local defined. It is well defined globally since transition functions are Casimir function mentioned before. The generalized holomorphic function always Casimir functions for this Prosum structure. Okay. So theorem. Let M be a generalized complex manifold in the L minus is eigenvalue for full G. If E is a generalized holomorphic vector bundle on M, there exists a L minus connection, a partial bar L on E such that partial bar L square equals 0. That is, E is Lie algebraic L minus module. This means this connection is flat. So to define this connection, from gamma E to gamma L plus tensor E, same in the holomorphic case, we define locally define just partial bar L X on the section locally, just define sigma D minus F lambda tensor E lambda. It will defined globally because the transition functions are generalized, the holomorphic functions. So this local defined flat connection is well defined globally. This square is 0 because D minus square is 0. This definition of the algebraic L minus. So this is flat. So this is more generalized holomorphic bundles. This by Marco Gualtieri. He defined this generalized holomorphic bundle in his PhD thesis. Is that a generalized holomorphic bundle on a generalized complex manifold is a vector bundle with the algebraic L max module structure. That is, there's a connection, a capital D bar from a section of E to section of L plus tensor E, such that D bar F S equals D minus F S in the F D bar S, and the D bar square 0, D bar square 0. So this is so we defined the generalized holomorphic bundle is special case of this more general definition. There are some interesting structures in this general case. For example, co-Higgs bundle structure, but there is in general no generalized complex structure on this total space E. It's out of the category of generalized geometry. So it is natural to ask the following question: under what conditions the total space E of a generalized holomorphic bundle admits a generalized complex structure such that capital D bar equals partial L, partial bar L. This is the flat connection in our special case. So what is the structure on the total space E in general? It's out of category of generalized geometry. Maybe there's more generalized geometry, but I don't know. Who knows? So it seems that the geometry structure on E is closed to the Prosum structure. So a section of generalized holomorphic bundle now return to our special case. So a generalized holomorphic bundle E partial bar L is called generalized section if partial bar L equals 0. That is, E is a parallel section respect to the canonical flat connection. So choosing a compatible local trivialization, a section S can be written in the tube functions x1, xr. So then the section S is a generalized holomorphic section if in the only F, O component Si are generalized holomorphic function on U. So this is second definition, local definition of generalized holomorphic section, just that after trivialization, each component is a generalized function. Another equivalent definition of a generalized holomorphic section is that it is generalized holomorphic map in sense of Aureni and the Pelli. This is an intrinsic definition, just like in an ordinary holomorphic case, a holomorphic section is a holomorphic map from M to E. So remark the notion of generalized holomorphic section can be also defined for Marcus general case by defined D bar S equals 0. By this by definition, so this also the generalized holomorphic section is also the OM module. Now give two special holomorphic generalized holomorphic bundle associate it with the generalized complex structure. So give a regular generalized complex manifold. That G star M is a section of our manner space. A cotangent bundle is a generalized holomorphic vector bundle on M, which is called the generalized holomorphic cotangent bundle of M. Similarly, GM defined as L plus intersection of L plus with TM is also generalized holomorphic bundle, which is called generalized holomorphic tangent bundle. So,
Professor Liu, can I ask? Can you remind us what is a regular generalized complex manifold?
The projection to Tm is a bundle.
Thank you.
This is a direct structure. So this is the bundle. Regular means this is a bundle.
Thank you. Yeah.
So in particular, holomorphic section of generalized holomorphic tangent bundle is called the generalized vector field. In the generalized holomorphic section of cotangent bundle is called generalized holomorphic one form. They are pairing, obviously, they are pairing a generalized function. So when M is manifold, we have G star M just the generalized holomorphic cotangent bundle, just the holomorphic generalized homomorphic cotangent bundle, and the GM is just holomorphic tangent bundle. When M is symplectic manifold, both G star M and the GM rank is 0. This is a graph. Since this rank is 0, this is trivial, it's nothing. So for regular holomorphic Prosum manifold, the GM is holomorphic tangent bundle, and the G star M is the kernel pi intersection of kernel pi with a general with holomorphic cotangent bundle. Two remarks. Regularity is not essential. One can also define G star is a sheaf model of OM in singular case. So in our case, both G and G star vanish in simplistic case, but we can, by taking a general complex space, CK cross R2R is a fiber of a generalized holomorphic bundle. One can define non-trivial generalized holomorphic tangent bundle in the cotangent bundle for simplistic manifold. In our case, the fiber of generalized vector bundle only a complex vector base, but maybe more general definition of generalized holomorphic bundle plus real part. So now the jet bundle of generalized holomorphic bundle is usual. It's for a generalized holomorphic bundle, define at a point the two holomorphic section is equivalent if phi m equal psi m in the tangent map is same. So at any point, the fiber of a jet bundle is phi square is equivalent class phi square bracket. That's right. In local coordinates, in order adjust the phi in the psi equivalent, just the value same in the first order derivative is same. So this is the Euro definition of jet bundle. Jet bundle. So we have proposition jet bundle of generalized holomorphic bundle on M. It fits into a short exact sequence. It is itself is also a generalized holomorphic bundle, and we have a short exact sequence of generalized holomorphic bundle. This generalized holomorphic is generalized holomorphic. Yeah, this jet, because this is a jet sequence this also makes sense. Is the shape of module over OM in singular case. Yeah. So now define the generalized holomorphic connection. So a generalized E is a generalized holomorphic bundle on the generalized complex manifold. M, a generalized holomorphic connection on E, is a complex linear map from E to E star M at tensor E. Here we use shift language since we can include more general case in the singular case. This definition is also makes sense. So we use shift language so satisfy the DFS equals D plus F tensor F. So this is also considered the section of F. So here E is E in the G star M denotes the shape of generalized holomorphic sections of E. And by definition, the D plus F in L minors. So we can get if for holomorphic generalized holomorphic function, D plus F is a generalized holomorphic one form on M. Yeah. So lemma, let E be a generalized holomorphic bundle on E. A complex linear map is generalized holomorphic if in the only F, the derivative along each generalized holomorphic vector field preserves generalized holomorphic section of E. Yeah. So in three cases, when M is a complex manifold, generalized holomorphic connection is just the generalized connection. When M a simplistic manifold, it's nothing. When M is a holomorphic prosum, so a generalized holomorphic connection is a holomorphic connection such that dx equals 0 for any Hamiltonian vector field on M. In other words, the connection one form takes value in the kernel of pi. So now we are in position to define Atiyah class, the obstruction of existence of generalized holomorphic connection. The first one is the first by Cech cohomology. Everything similar in the ordinary holomorphic case. This we get one cocycle. Here we change the holomorphic in the generalized holomorphic pattern in the partial change into D plus. That is almost similar. The product is similar in similar to the ordinary holomorphic case. So in this case, we define Atiyah class AE, and is one this cohomology class for this one cocycle in this instance in the coefficient is G star M tensor EM and EM, where D plus is the Lie algebra differential of I eigenvalue bundle L plus. So theorem, let E a generalized holomorphic bundle on a generalized manifold. M then E admits a generalized holomorphic connection F in the only F, the Atiyah class AE is zero, vanish. So this first approach to define Atiyah class, second by extension class. So when M is regular, in fact, it's not essential, not necessarily regular. So general complex manifold, we have another definition to define Atiyah class. We call that the jet sequence is a short exact sequence of generalized holomorphic bundle on M. So definition, for a generalized holomorphic vector bundle E of on a regular generalized complex structure, complex manifold M, Atiyah class of E is defined as the first extension class of this exact sequence. So by definition, the class is trivial, is zero, is equivalent. This exact sequence can be splitted. So it follows theorem is generalized for a generalized bundle E on a regular generalized complex manifold M. Then E admits a generalized holomorphic connection F in the only F. Atiyah class is zero. So that is the jet sequence is split into E, direct sum with G star M tensor E. Split is follows. This is a general correspondence between this phi. This is a phi section of E in the square bracket phi is a section of jet E. There's a standard correspondence between section of E and a section of jet E that satisfies the following relations. So by this correspondence, the splitting of jet E is one corresponding with generalized holomorphic connection E. This relation is follows. So this is a second way to for Atiyah class. Third one is by Lie pair. Lie pair, we have maybe 2 minutes of the Lie pair is a pair of Lie algebra. Lie algebra L and A with A module, A module in the vector flat A connection that extend this flat connection A to L connection, Napla. The curvature is a bundle map, or Napla from vector to L to in the E, such that R not is zero, since this A module, flat A contained in the we get a map from A to A per a tensor E in the E. A per is a dual bundle of L quotient A. It's a bundle L star. So proposition. So this from Lie algebra. So R Napla is a bundle map for, from Lie algebra A to its module A per tensor in the E. So proposition is R Napla is a Wankel cycle. The cohomology class is called Atiyah class. This is defined by Chen, Stienon and Xu. In the Xu, this class is independent of choice of extension, extension of Napla. So this class zero is equivalent that exists a Napla such that the mixed term of curvature is zero. So for a holomorphic vector bundle, this is the ordinary, ordinary holomorphic vector bundle E in the partial bar on the complex manifold, the Atiyah class of Lie pair, Tm in the T0 1m is just that one given by Atiyah, this already mine. So in our general case, next late E partial L is a generalized holomorphic bundle and a regular, not necessarily regular, generalized manifold M. Thus, the T star M in the rho L minus is a Lie pair. Rho is anchor from generalized tangent bundle to tangent bundle. So this is Lie pair. So in the E is also a rho L minor module induced from L minus module structure. Note that the pore of rho L minor is just L intersection of L minor intersection with intersection of L minor with cotangent bundle. Is the definition of a G star M generalized holomorphic tangent bundle. This is true by since L is Dirac structure, maximum isotropic bundle. Therefore, we have Atiyah class for Lie pair. AE is from rho in the G star M with coefficient G star M in the tensor EM. This theorem is a theorem of theorem. This Atiyah class vanishes if in the only if there exists a generalized holomorphic connection on generalized holomorphic vector bundle. So far we have defined the Atiyah class AE by three approaches: Cech cohomology, extension class of jet, first jet bundle, as well as Lie algebraic cohomology of a Lie pair. Their common property is that AE equals 0 if in the only if there exists a generalized holomorphic connection on the generalized holomorphic bundle E. For complex manifold, these three cohomology groups are isomorphic. But in our general case, their relations are not clear for us so far. So that's all. Thank you. Thank you for your attention.
Okay, thank you. Thank you, Professor Liu. Are there any questions? So in the case of a holomorphic Poisson structure, are there natural examples of holomorphic of E, and for which you want to know? So what are natural examples? Is the kernel of pi sharp? Is that a?
No.
The kernel of pi sharp is the G star. The G star M is always a generalized holomorphic vector bundle.
Maybe so far, we didn't construct any non-trivial examples.
And the three classes you have defined, you said you don't know in general whether they are the same, or but in the case of symplectic,
it's trivial. It's trivial.
So the G star M is 0 there.
Yes. So in regular case, it's so in ordinary holomorphic case of a complex manifold, these three cohomology groups are isomorphic. But in general case, we don't know. So far. Maybe it seems in regular case, it seems some close relations among these three cohomology groups, but it's difficult to treat for a general case.
Mm. Mm. Thank you. Are there any other questions?
I have a question.
Okay.
In a holomorphic case, you can take the powers of the Atiyah class and take its trace to define Chen classes.
Yeah.
Is there something similar in the generalized holomorphic case?
Yes, just our last way Lie pair. This Lie pair. So Chen is just I mentioned that in beginning of the talk, it's just corresponded by Chen connect just corresponding to this Lie pair,
Mm-hmm.
So in this case, is set by the curvature to 0, mixed term is 0.
So I'm curious about the case where if you have a manifold where you can deform the generalized complex structure from being holomorphic to symplectic, then in the symplectic case, the Atiyah class must vanish, right? Because your bundle G is 0.
Yes.
So if you had defined some sort of Chen classes, there would be 0 in the symplectic case. Is that correct?
Not in symplectic case. It's trivial. It's trivial. So can do nothing. So just this remark. We have a remark. Maybe we should define more general of generalized complex holomorphic bundle plus such that the bundle let me no so in our case, the fiber of a generalized holomorphic bundle is the complex space. So for simplex case, this is trivial. Maybe one can define the holomorphic generalized holomorphic bundle with fiber is generalized complex space, including real part. Then we can treat the simplex case non-trivial.
So the issue is the bundle is not varying holomorphically or even continuously. Yeah, I see. All right, thank you.
Okay. Are there any other questions?
Yes, please.
Fatima.
Yes. Hi.
Hi.
Yeah.
I was wondering, so there was some recent work, I think, by Liu, Stienon and Xu, who defined the Atiyah class of a differential graded manifold. So it's actually, it's quite an elegant construction. So I was wondering if this could be applied in your situation, to shed some light on some of the questions you were posing at the end. I don't know, are you familiar with that work?
Sorry.
I was just asking if you've looked at this work of Liu, Stienon and Xu.
I know. There's a work on DG manifold.
Yes. So is this something that you think could apply in your situation, generalized?
Not yet. Maybe in future.
Okay. And then I was also wondering, so in this generalized complex structure business, you can also twist them by a closed form on your manifold, which I think throughout your talk you assume to be equal to 0. What if it's non-zero? Does your construction still apply in that case?
Okay, maybe try in the future.
Okay, thank you.
Thanks.
Great. Okay. And any sorry, I was muted. Are there any, sorry, I was asking whether there was any more questions. I was muted. Okay. So if not, let's thank Professor Liu again for the very nice talk.
Thank you.
Okay, great. So I think next week there will be, it'll continue next week. Yeah.
Okay. So
all right.
Thank you.
The seminar will continue next week. Yeah. Okay, great. Thanks to everyone for coming.
Thanks.
And thanks
Bye-bye.
to Professor Liu again.
Bye. Bye.